Hello students. Let me start with a question. How do you describe how fast a car is going? Simple, right? You just look at the speedometer. But what if you also want to know where the car is heading? Now you need more than just speed. You need velocity. Speed tells us how fast something is moving. Velocity tells us how fast and in which direction. And that little difference makes a huge impact in physics. So today, we'll learn how these two motion descriptors help us understand how objects move in the real world. Let's begin with speed. In physics, speed is defined as the rate of change of distance with time. The formula is speed equals distance divided by time, or simply, v equals s divided by t, where v is the speed, s is the distance traveled in meters, and t is the time taken in seconds. It's a scalar quantity, which means it has magnitude only, not direction. That's why if two cars are moving at the same speed, but in opposite directions, their speeds are still equal. If a body covers equal distances in equal intervals of time, we say it is moving with uniform speed. For example, the motion of a ball on a frictionless surface is uniform, smooth, consistent, and predictable. Speed isn't always constant, so we use two terms: instantaneous speed and average speed. Instantaneous speed is the speed of the body at a particular instant. Think of the number shown on a car's speedometer. That's the instantaneous speed. Now, average speed is defined over a journey. It is average speed equals total distance traveled divided by total time taken. Say you travel 150 kilometers in 3 hours. Your average speed is 150 divided by 3. That is 50 kilometers per hour. If the motion is uniform, instantaneous speed equals average speed, but in real life, vehicles often accelerate or slow down, making the two different. Let's now introduce velocity. Velocity is like speed, but smarter because it also includes direction. That's why it's called a vector quantity. Velocity equals displacement divided by time, or v with an arrow over it equals s with an arrow over it divided by t, where s with an arrow over it is the displacement, and t is time. So if a car travels 100 meters east in 5 seconds, its velocity is 20 meters per second east. Because it has both direction and magnitude, velocity changes even if speed stays the same as long as direction changes. Uniform velocity means equal displacements in equal intervals of time, always in the same direction. Velocity can be of two types: uniform and non-uniform. In uniform velocity, both speed and direction remain constant, like a car cruising straight down a highway. But in non-uniform velocity, either the magnitude or direction or both change. Imagine a car turning around a circular track at constant speed. The direction is always changing, so the velocity is changing. So even though the speed remains the same, the velocity is variable because it's a vector and direction matters. This is exactly what happens in circular motion shown in figure 2.5, where at points A, B, C, and D, the direction of the velocity vector changes continuously. Now let's understand instantaneous velocity and average velocity. Instantaneous velocity is the velocity of the object at a specific moment. It's like looking at your GPS showing you're moving 40 kilometers per hour west right now. Average velocity, on the other hand, is displacement divided by total time taken. Even if you take a curved path, average velocity only cares about where you started and where you ended up. Here's a surprising fact. Your average velocity can be 0, even if you traveled a lot of distance. If you go from your home to a park and come back, your displacement is 0, so average velocity is 0, even though your average speed is not. Let's wrap up by comparing speed and velocity side by side. Speed is scalar, velocity is vector. Speed tells us how fast, velocity tells us how fast and where to. Speed is always positive. Velocity can be positive, negative, or 0 depending on direction. Here's an example. A ball is thrown straight up. On its way up, its velocity is upward. At the top, velocity becomes 0 for a moment, and on the way down, velocity becomes downward. But at every point, the speed is still a positive number. This difference is crucial, especially when we calculate acceleration or study projectile motion later on. So to sum up, velocity gives us a much richer understanding of motion than speed alone. I hope you now clearly understand how speed and velocity differ and why vectors make physics much more interesting. In the next session, we'll take this forward and explore acceleration, how motion changes over time. Until then, keep observing the motion around you. See you soon.